Okay, in this video, we're about to talk about radius of convergence, but I wanted to pull up some Desmos to give you some background of what I'm talking about here. So we've talked about radius of convergence before when we had geometric series, where a geometric series converges whenever r is between -1 and 1. And sometimes that window was wide, and sometimes it was small, because we had things that would like shift over. So instead of going from -1 to 1, it might go from like 0 to 2. Or if my ratio, if r was like 2x, that -1 to 1 became -1/2 to 1/2, and it shrunk. But basically, I can have a radius of convergence that just kind of goes from side to side and stops. And you can kind of see that here. Here's 1 over 1 minus x, and here's the geometric series it creates, 1 plus x squared, because of that a over 1 minus r. And even if I add x to the 6th in here, and add an x to the 7th, I'm still not getting much closer beyond -1 to +1. But if you take a look at something like sine x in the series for sine x, already I'm out -3 to 3, and I'm only at the x to the 7th. If I add x to the 9th divided by 9 factorial, now I've gotten closer to 4. If I add an x to the 11th divided by 11 factorial, or really subtract 1, now I'm past -4. And we've talked about if I kept going here, I could make this fit all the way out to -infinity to infinity. So a radius of convergence is variable depending on your series. So now we're going to get to the notes. There are technically 3 options for a series with respect to convergence. Let me flip my computer here. So my 3 options for a series are going to be: it converges for all values of x. That would be like y equals sine x, where eventually you could fit everything. It converges on a certain interval. That's often like your geometric series, okay? Not just those, but that's what you know so far. And then the last option that doesn't come up that often, but it does come up, is that the series converges at x equals a only. In other words, you could basically be tangent and try to bend it to make the tangent better, but it's never going to be very good. Now, again, this does not come up often, but it does come up, and it's just basically the idea that you can have something where it touches once, and beyond that, you can never get it to really hug the curve. So to find the interval of convergence, if it's geometric, we can do that geometric a over 1 minus r thing to get the function I'm modeling, and then put r between 1 and -1. If it's not geometric, we have to use this ratio test. Now, by the way, this ratio test still works if it's geometric. It works on everything, but this is a big deal. This is something that's going to keep coming back. Wow, I can't speak. And the ratio test says this: if you have a series, and that series is like a sigma of a sub n's, if you take the limit as n approaches infinity of a sub n plus 1 divided by a sub n, it should equal some limit. Your series will converge if that limit is less than 1. Now, why does that make sense? Well, if my series is less than 1, that means this is less than 1, which means the top is smaller than the bottom, which means later terms are smaller than earlier terms. Now, why does that matter? It matters because when we talked about a long, long time ago, it all comes together. Remember how we had like y equals 1 over x, and then I showed you could integrate that, and the area ends up being infinity, as opposed to e to the -x, and if you integrate that, it doesn't go to -infinity. It's the idea, or pardon me, it doesn't go to infinity. It's the idea that when you have all these fractions for 1 over x, a half, a third, a fourth, a fifth, those are actually really close together. Where if I had like e to the -x, that'd be 1 over e squared, 1 over e cubed. And e is like 2.718, right? So this would be like 1 over 2.718. E squared is 1.738, and e cubed is 1/20th. So I'm going to go 1 over 7, 1 over 20. There's a big gap there. And because my later terms are smaller than my prior terms by a significant margin, when I add them together, I get a convergent sum. So the idea behind this ratio test here is if I can definitively show that my later terms are less than my smaller terms, it has a chance at convergence. Now, the series will diverge if L is greater than 1, because if later terms are bigger than earlier terms, it's going to grow to infinity. And if L equals 1, the test is inconclusive. Now, for what we use this for, I don't care about B or C right now. I'm just going to go through one example with you so we can get something under our belt, and then we will talk face to face. Now, I love the ratio test because the ratio test is super fun, and you get to cancel things out like factorials, and it's so much fun to cancel factorials and exponentials. I get really excited. Now, that's kind of like a normal day for me, but this is exciting stuff. So if you want to find the ratio test to find the interval of convergence, you take the limit as n approaches infinity of a sub n plus 1. This is technically a sub n. So if I want a sub n plus 1, I replace all the n's with n plus 1. See what I did there? All the n's became n plus 1's. So if I'm going to take the limit of a sub n plus 1 divided by a sub n, I'm going to need a big thing here. A sub n plus 1 is really n plus 2 over 3 to the n plus 2 times x to the n plus 1. And a sub n is that original, n plus 1, 3 to the n plus 1, x to the n. I want